So in the last section we have discussed about reflection of light and what phenomenon occurs during the reflection of light and how the reflection occurs through a plane mirror and a spherical mirror, and where the image is formed by the reflection of light. Now a new topic, new chapter, that is refraction of light. It is refraction of light. And first I will define, or we will know what is this refraction of light. What do we mean by refraction of light? So what is this refraction? It is a phenomenon of change in the direction of the path of the light when it travels from one medium to another medium, right? So we can say that the phenomenon of change in the direction of the path of light, the phenomenon of change in direction of the phenomenon of change in the direction of path of the light, when it travels from one medium to another medium, This is called refraction. The phenomenon of change in direction of the path of the light. The change in the direction of the path of the light when it travels from one medium to another medium. Means from here we conclude that when a light travels from one medium to another medium, it changes its path. What is the original path with which it is coming in one medium? When it enters to the other medium, then it changes its direction of the path. Now, so this one, let us consider how this occurs. So let us consider this is a medium 1, and there is another medium 2. There are two media, medium 1, medium 2, and this boundary is called interface. This is the interface of the media, interface of the two media. This is the interface. And when if we draw, this is the normal to the interface. When a ray of light incident travel from medium 1 to medium 2, if there is no interface, this should be the original path. There is no change in path. If there is no boundary or interface, the same medium or the medium 1 or medium 2, both are in the both sides of the interface, then this is the actual path. So this is the incident light. When it travels from one medium to another medium, it changes its direction like this. It travels along this path. Or it may change along this path. Any path it changes, means it will not travel along the same path. It changes its direction of the path of light. This is called your refraction. Means it travels from one to another medium, it changes its direction of the path. So here we can say, let this x dash, x and x dash, this is the interface, means the boundary of two media. This is medium 1, medium 2. AO is the incident ray. AO is the incident ray. N O and S, NO and S, normal, perpendicular to the interface, perpendicular to the interface. OB, OB, refracted ray, refracted ray, refracted, because it is refraction, so it is refracted ray, OB. Normal to the incident ray, this angle, I, here I is the angle of incidence, angle of incidence. R, normal, this is the normal, this angle, R, angle of refraction, angle of refraction. Clear? So these are the terms we will consider in a refraction. Incident ray, normal to the interface, refracted ray, angle of incidence, angle of refraction. Right? Now, how this ray bends to the normal or if they bends away from the normal. The ray, the refracted ray, you can show like this in this region or in this region. Means if the ray is refracted in this region, we can say the refracted ray bends toward the normal. If it is in this region, we can say it is refracted away from the normal. That depends on the nature of the two media. The nature of the two media. Let me show that how this you can say how it bends like that. Let us consider a ray travels from a optically denser to rarer and a rarer to denser. Two cases we will show here. Let us consider. So let us consider this is the interface X dash X O X dash and this is a normal. In this figure you can show that this X dash and this is the normal with that normal and M dash is the normal and M dash is the normal. Right? So now consider a ray is traveling from, suppose this is a rarer medium and this is a denser medium. In this figure, let this is a denser and this is a rarer. Now what this refraction says, as we know that, then the ray incident travel from rarer to denser. Then this will be the actual path if there is no refraction. But this dotted line is the actual path if there is no refraction. Here also, this is the incident ray and this will be the actual path. Right? This is the incident ray and this will be the actual path. And what is this incident angle? Normal to the incident ray, this is the angle of incidence. Here this is the angle of incidence. Now come to this case. Now the ray is traveling from rarer to denser. When the ray traveling from rarer to denser medium, in that case what happens? The ray bends towards the normal. Means towards the normal means the ray will be positioning in between these two lines. This is the refracted ray. And this is the angle of refraction R. When the ray is traveling from denser to rarer, bends toward the normal. You can say bends toward the normal. So in this case, bends toward the normal. When the ray traveling from rarer to denser. In this case, when it traveling from denser to rarer, it bends away from the normal means the ray will in this region. away from the normal, and this angle is called angle of refraction. So here bends away from the normal, bends away from the normal. When the ray is traveling from radar to denser, when you see this one, in this case, angle of incidence is greater than angle of refraction, isn't it? Angle of incidence is greater than angle of refraction. I is greater than R. So let me show like this is I is greater than R. But here I, angle of incidence, is less than R. Here angle of incidence is less than R. Means a ray is traveling from denser to rarer, the angle of refraction is denser to rarer, the angle of refraction is greater than angle of incidence. But in this case, I is greater than R. Next. So in this is the case. And how this occurs, you know that. And the rays already you know that this is the incident ray in both the cases. OB is the refracted ray. Here AO and OB. And the angle of refraction. So this is the refraction when a ray is traveling from rarer to denser or from denser to rarer. That is should remember. Clear? Now the question is here, why this refraction, why the direction of the path of the light changes? Why this refraction occurs? When the ray travels, why it changes its path? As you know that when a ray is traveling from one medium to another medium, its speed changes. Its speed changes. And as we know that the speed of light is greater in rarer and less in denser. So the speed of light in the rarer medium is greater than speed in the denser medium. The speed of light in rarer medium is greater than the speed of light in denser medium. Means here the speed of light is more, here the speed of light is less. Here the speed of light is less, here it is more. So when the light travels from one medium to another medium, it moves from one medium to another medium, it interacts with the medium particles. And its speed changes. And then in the denser medium, the interaction is more. In rarer medium, the interaction is less. So because of this interaction of the light with the medium particles, its speed changes. Because of change in speed, it changes its path. Because of the change in speed, it changes its path. Suppose I change my speed, then I can change the path of my path. Okay. So this is the cause of the refraction of light. Okay. Then next part is that after this we will go to the another one. Another point, remember always, when a interface is there, is there any interface like this, and this is a normal, and XOX dash is a interface medium 1 and 2, maybe denser or rarer. If a ray of light incident normally and travels from one medium to another medium, it does not change its path. Means the refraction can occur only when the light incident obliquely, means make some angle with the normal to the interface. If it incident normally, it goes undeviated. Remember this. When a ray of light incident normally on the interface, it goes undeviated. It does not change its path. So undeviated. Here it deviates from its path. Here it deviates from its path. But here it does not deviate from its path. Okay. Then we will go to the most important term associated refraction that we will always discuss. That is the refractive index. Next, another one we will discuss about the refractive index of a medium. Refractive index of a medium. What is the refractive index of a medium? So here first we will discuss what is the refractive index of a medium. First we will discuss about the absolute refractive index. Absolute refractive index. Absolute refractive index. Then we will go to the another refractive index. Absolute refractive index. So absolute refractive index of a medium can be defined as the ratio of speed of light. The absolute refractive index of a medium can be defined as the ratio of speed of light in a medium to the speed of light in that medium. The absolute refractive index of a medium can be defined as the ratio of speed of light in air medium or vacuum medium to the speed of light in that medium. So this is the speed of light in air, or we can say that is the vacuum. Then I will consider this air or vacuum to the speed of light in that medium, for which we are calculating the absolute refractive index. For which we are calculating the refractive index. Means here in this case, if a ray is there, this medium should be air medium and this is any other medium. Any other medium. And the ray travels from air and enters to this medium. And the ray enters to this medium. So the speed of light in this medium, in the incident ray is in the air medium. The refracted ray is in that medium for which you are calculating the refractive index. Remember, for absolute refractive index, the incident ray should be in air medium and the refracted ray should be in that medium, for which you are calculating. Take the ratio, that ratio is the absolute refractive index. Here, and as you know that when this, the speed of light in air or vacuum is always greater than the speed in that any other medium, because it is the speed is more in a vacuum, that is 3 into 10 to the 8 meter per second. So it is always greater than V. If C is always greater than V, then mu is greater than 1. Then mu is greater than 1. It means what? The absolute refractive index of a medium is always greater than 1. Because practically we don't know any other medium where the speed of light is more than air medium. So C is greater than V, then mu is obviously greater than 1. So mu is obviously greater than 1. Clear? Now, and remember one thing, the absolute refractive index has no unit and dimension. It has no unit and dimension because it is speed by speed. That cancel. Then next one, the relative refractive index. Next one is the relative refractive index. What is this relative refractive index? For relative refractive index, replace this air medium. Take the medium 1 here and this is the medium 2. Now the ray is traveling from medium 1 to medium 2. This is the angle of incidence and this is the incident ray AO, and OB is the refracted ray and this is the angle of refraction, as you know. And this is a normal and O and this. When the ray is traveling from medium 1 to medium 2 and let the speed of light in medium 1 is V1 and the speed of light in medium 2 is V2. It changes its speed from one medium to another medium. So let V1 is the medium speed in medium 1, V2 is the speed in medium 2. When you calculate the refractive index mu R, that we can written like this: relative refractive index mu R is equal to the speed in the medium 1 divided by the speed in medium 2. Means when you say relative refractive index, then the air medium is replaced by any other medium, that velocity divided by the second medium. Then it is called relative refractive index. Relative refractive index. Clear? So the relative refractive index of medium 2. So how we read this one? This can be written as mu R. Here you can write the refractive index of second medium with respect to first medium. Remember, this notation is very important. Relative refractive index means, how we read this one? Relative refractive index means refractive index of medium 2 with respect to medium 1. It can be read as refractive index of medium 2 with respect to medium 1. How to know that? Where we will put that 2 or 1 means where the refracted ray, in which medium the refracted ray, in the medium 2. So we will know the refractive index of 2. From where it comes? Medium 1. It comes from medium 1. So this is medium 1. So mu2 means it will be written like this. This is the relative refractive index. So what do we read that? Relative refractive index means the speed of light in medium 1 to the speed of light in medium 2. And what we read that is the refractive index of medium 2 with respect to 1. Suppose this is medium 2 and this is medium 1. Then what we will write? Let me make that medium. This is medium 2 and this is medium 1. And here the speed is suppose v2 and here the speed is suppose v1. Or in medium 2, let me take a notation v1, here is v2. How we find? Now the refractor is in which medium? In medium 1. So I will make it like this. Refractive index of medium 1, from where it comes? Medium 2 is equal to the speed in which medium? The speed of light in which medium? When 2 to 1, we are v1 by v2. Now when it v1 to v2, then this medium 2, so it is v1 and here it is a v2. So v1 by v2. But we will write like this. Refractive index of medium 1 we read with respect to medium 2. That equal to the speed of light. The speed of light from where it comes? From medium 2. Where its velocity? v1 divided by v2. Means from where it comes, that speed divided by to which medium it goes, divided by that. So this is called relative refractive index. And remember one thing, a medium having high value of refractive index is optically denser and lower value of refractive index is optically rarer. Okay? So a medium having high value of refractive index is optically denser, and the medium which has less value of or smaller value of refractive index is optically rarer medium. Then another thing you will find here, the relative refractive index of the relative refractive index. For that we will find some relation, a relation on relative refractive index. Now we will put the formulas like that. Now what we will do here, I will find an expression for relative refractive index. How we find this? See, let us consider, we will find a relation after knowing the relative refractive index. Suppose this is the XO express and this is the normal and NS, and let a ray of light incident and it refracted and it refracted. AO is the incident ray, OB is the refracted ray. Okay? Let the speed of light in this medium is V1, the speed of light in this medium is V. Clear? And let this is the medium 1, and this is medium 2. Clear? So as you know, now if you put that, what is the relative refractive index of 2 with respect to 1, medium 2 with respect to 1? That should be equal to V1 by V2. That equal to V1 by V2. Clear? Now I can write this expression as this is equal to C by V1, C by V2 divided by C by V1. Can you write like this from here to here? multiply C and divide C. C by V2, that equation is same. C by V2 divided by C by V1. So what is the C by V2? C by V2 is called, this is the absolute refractive index, speed of light in the air to medium 2. V2 is the speed in V2. When it is the air medium, that is called absolute refractive index of second. You don't need to write relative because this is air medium. So you can write mu2 divided by absolute refractive index of medium 1 with respect to air, that is the absolute. So mu2 by mu1. So you can say mu21 is equal to mu2 by mu1. This is another relation. Clear? So see this is the another relation. So we can write this as the refractive index. We can write mu21 is equal to V1 by V2, which should be equal to, according to this, mu2 by mu1. This is also a relative. So this is the form in terms of speed, and this is the relative refractive index in terms of absolute refractive index. These are the relations. Okay. Then, if there is a multiple refraction, then from this relation we can say another form like that. Now, from this relation, we will get another equation like this is one medium. So this is velocity speed V2. Let us consider there is another medium. This is another medium y dash, and this is the another boundary, another interference. Now, in this case, for this one, so this is n dash. Now the ray is in this medium 2, then it travels to medium 3. This is medium 3, where the speed is v3. It travels from medium 1 to 2, then 3. Now let this is the normal. Now it bends like this in the medium 3. From medium 2 to 3, when it travels from medium 2 to 3, it bends like this. So this is the multiple refraction. Number of times refraction occurs from the 3 media. So in that case, how we find the relation? Now we take this mu2 second with respect to first one, medium 2 with respect to 1. So according to formula, v1 by v2. The refractive index of 3 with respect to 2. If from 2 to 3, 3 with respect to 2, then what will put? This is equal to v2 by v3. From 2 to 3 means where first is what? In which medium the incident ray? In these two media, this is the incident ray, this is the refracted ray. For these two, this is incident ray, this is refracted ray. So mu v2 by v3. Now, if you multiply that, mu21 into mu32, that equal to v1 by v2 into v2 by v3. So this can be v1 by v3. What is this v1 by v3? What you can write? Refractive index of which medium? 3 with respect to 1. 3 with respect to 1. That means 2 with respect to 1 into 3 with respect to 2 refractive index equal to, this is another relation. And there is a number of refraction. Similarly, if another medium is there, fourth medium, M4, then simple thing is that, see the relation how I write. For fourth with respect to 1, there are multiple refractions, there are 4 media. Then you can write the relation like this. See, 2 to 1 into refractive index of 2 to 3, second to third, into refractive index of 3 to 4. So the ray is traveling from 1 to 2, 2 to 3, 3 to 4. That we can write as 4 with respect to 1. This is relating the refractive index of different media. Okay. Then after knowing this one, let us go to the laws of refraction of light. The most important one is the, after knowing the refractive index, now come to the laws of refraction of light. Next come to the laws of refraction. Laws of refraction of light. Like the laws of reflection of light, here also the laws of refraction of light. So the law 1, there are 2 laws again in the law of refraction. The law 1, what it says? Like the same thing in the reflection, the incident ray, the refracted ray, and the normal to the interface, and the normal to the interface at the point of incidence lie on the same plane. Lie on the same plane means they are co-planar. The incident ray, refracted ray, and normal to the interface at the point of incidence all lie on the same plane. Here is the interface, normal at the point of incidence, incident ray, normal to the interface at the point of incidence, and this is the refracted ray. All lie in which plane? On this whiteboard. I have drawn all these things on this, means on this two-dimension figure I have shown all this, and they are in the same plane, means they are co-planar. Okay, this is the law 1. Then law 2. At the law 2, this is the angle of incidence, this is the angle of refraction. But the law 2, the law 2 is the ratio of the sine of angle of incidence to the sine of angle of refraction. The ratio of sine of angle of incidence to the sine of angle of refraction is constant for any two given media. For any two given media means the ratio of sine of angle of incidence to the sine of angle of refraction is a constant for any two media. Right? For any two media. And the second law, the ratio of sine of angle of incidence to the sine of angle of refraction is a constant for any two media. Means I can write sine of angle of incidence to the sine of angle of refraction is a constant. And this second law is also known as Snell's law. This is also known as Snell's law. Right? So if I ask you state Snell's law, you will say this one. The ratio of sine of angle of incidence to the sine of angle of refraction is a constant for any two media, and this constant is called the refractive index. This constant is called as the refractive index. Which refractive? The relative refractive index. Here it is the medium 1, this is medium 2. So this constant is the relative refractive index 2 with respect to 1, because the ray is traveling from 1 to 2. So this is the relative refractive index of 2 with respect to 1, and this is your Snell's law. The constant is equal to relative refractive index of 2 with respect to 1. Okay. Or you can write this again in another way. So in this case, sine I by sine R, the Snell's law, according to this second law, or you can say this is the Snell's law. So according to this Snell's law, sine I by sine R is mu 2 with respect to 1. Relative refractive index of 2 with respect to 1. And remember, while writing relative, where the refracted ray, that first write, right? At the refractive index of 2 with respect to 1. So this is sine I by sine R. Clear? Now I can write this is equal to sine I by sine R. I can write this is equal to mu to 1. If you write this in absolute refractive index, mu 2 with respect to 1. So if I write this in terms of absolute refractive index, this is mu 2 by mu 1. Already know that mu21, mu relative, we have derived the relation mu2 to 1 is equal to absolute of second with respect to first. So if you multiply that, mu1 sin I is equal to mu2 sin R. This is also from the second law, from the Snell's law. Second law means from the Snell's law. Absolute refractive index of medium 1, absolute refractive index of medium 2, absolute refractive index of medium 1, mu1 into sine of angle of incidence in the which that medium, in medium 1 whose refractive index is mu1, the incident ray is there, it makes an angle I. So mu1 sin I is equal to mu2 sin R. This is from the Snell's law. Okay. So if the first medium is vacuum or air medium, then the refractive index is given by which? If the first medium is air medium, then you can write what? Sin I by sin R is equal to absolute refractive index of 2. Then we write like this, mu 2 1. Okay. The relation is like this. This is also Snell's law. This can be an air medium and this is any other medium. Okay. So this is your Snell's law and laws of refraction. And from these laws of refraction, we'll go to another one is the principle of reversibility of light. Another relation is the principle of reversibility of light. From this laws of refraction, by using these laws of refraction, all these things, we will go to another relation is the principle of reversibility of light. So what is this principle of reversibility of light? According to this principle of reversibility, if the path of ray of light, if the path of ray of light, if the path of a ray of light, if the path of a ray of light is reversed after, if the path of a ray of light is reversed after suffering a number of reflection and refraction, after suffering a number of reflection and refraction, a number of maybe one or maybe two, like that, one reflection or two refract, it takes the reflection and a number of reflection and a refraction, it retraces its path, This is the principle. The principle of reversibility states that if the path of a ray of light is reversed after suffering a number of reflection and refraction, it retraces its path. So how this happens and how this we will show. Let us consider there is a ray of light. This is an interface. This is the normal ray. Ray of light traveling from medium 1 to medium 2, and then the ray is refracted like this. This is the angle of incidence, this is the angle of refraction, and this will be the actual path, but the ray gets refracted when it travels from medium 1 to 2. From this figure you can say this is a rarer and suppose this is a denser. So this is one refraction of course. Now if I will place a plane mirror, on this, on the path of the refracted ray, a plane mirror like this, which is placed, the plane mirror is so placed that the refracted ray incident normally on this one, this is perpendicular, the incident ray incident normally. Then what happens? If the incident ray incident normally, then what you will find here? If the incident ray is incident normally, then it will do what? Now this ray incident normally, now here because I have a plane mirror, the reflection occurs and the reflection will be along the same direction. and the ray will retrace the same path. The ray will retrace the same path. The ray retrace the same path. This is the principle of reversibility. After reflection and refraction, here one reflection, one refraction. Here medium 1 to 2 refraction, here reflection. So after suffering a number of reflections and refractions, it retraces its path. In what path it is coming? It will retrace in the same path. Right? So from there, from this one, we will get a relation. We will derive a relation. So okay. And in this, remember in this case, in the as per the principle of reversibility, image and object position can be interchanged. The image and object position can be interchanged. If you consider there is an object, you will find an image, and the object changes to the position of image. Image can go to the position of object according to the principle of reversibility. Clear? Now by using this reversibility, let us find what is the refractive index of 2 with respect to 1. The rays traveling from 1 to 2. First the refraction, of course. Because of the refraction, what is mu to 1? That is equal to your sine of angle of incidence by sine of angle of refraction. Now after reflection, this is the first case. After reflection, what happens? The ray retraces. Now this is the incident ray and this is the refracted ray. Now the incident ray is in medium 2, the refracted ray is in medium 1. So what I will write? Refractive index of 1 with respect to 2. Where the refracted ray? The dotted red, the set 2 arrow marks. This is the refracted ray. This is the incident ray. The refracted ray is in which medium? 1. Incident ray is in medium 2. After reflection. After the reflection. So mu 1 with respect to 2. That equal to sine. Angle of incidence is now what? R. This is the angle of reflection divided by angle of incidence divided by angle of refraction. Here refraction is I because this is the refracted ray. For after reflection, this is refracted ray, this is a incident ray. Now you multiply these two. According to this one, now multiply. Multiply these two. Mu 2 1 into mu 1 2. What will we get? Sin I get cancel, sin R cancel. So we get 1. Or mu 2 1 is equal to 1 by mu 1 2. This is the principle of reversibility. The refractive index of second medium with respect to first medium equal to reciprocal of refractive index of first medium with respect to the second medium. So this is your principle of reversibility. Okay, by using this principle of reversibility, we will find some other relations. Okay, thank you.